Hey you! Yes you! If you like our video, just hit the subscribe button and also hit the bell icon to stay notified for the future updates. So hello everyone and welcome to Electronic Technocrat. So today's video will be completely based on, or we can say we'll be learning about another category of logic gates, that is the transistor logic gates. In the previous two videos which we have shown to you and which is described in the description below are based on simple diode logic gates. That's correct. And in this category we have two types. That is, the simple diode logic gates is divided into two types. Or we can say there are two gates involved in that category. The first one is the OR gate. That's correct. And the second one is the AND gate. That means you have watched our video. Thank you very much. So today we will be talking about transistor logic gates. Alright, so this will be our part number 3 of the logic gates. Yeah, there we go, the part number 3. And we are talking about transistor logic gates. So any guesses how many parts is it divided? That's correct. It's divided into 3 parts, or we can say 3 logic gates are involved in this. The first one is, yes, the NOT gate. The next one is the NOR gate, that is N-O-R. And the third one is NAND gate, that is N-A-N-D. That's correct. So we will study each of these gates one by one in each part of the video. So this part will be focusing on the NOT gate. Alright. So here you can see a symbolic diagram. Do you know which symbolic diagram is it? Or whose gate does it belong to? That's correct. Now let's guess. This box is left blank for you. I will give you 2 seconds, 3 seconds, 4 seconds, 5 seconds. Unable to guess? Well, the answer is pretty simple. The answer is, ta-da! The NOT gate. So we will be studying about NOT gate the whole video right now. Alright, so let's go. Okay, so the first question that rises in our mind before we start the NOT gate would be, what makes the NOT gate different, or we can say an exceptional case, when compared with the AND and the OR gate? Well, when you talk about AND gate or the OR gate, they belong, or they are involved with the simple diode logic gates. And the thing that makes NOT gate different from these two, or we can say exceptional case from these two, is the AND gate and the OR gate both have 2 inputs. You heard me right. Both have 2 inputs and 1 output. Whereas the NOT gate has 1 input and 1 output. Pretty simple, isn't it? Let's see what Tom Hanks says about this. Thank you, Tom Hanks. He's telling me great. Well, thank you, Tom Hanks. The answer is pretty much simple. I guess you get it. The AND gate and the OR gate has 2 inputs. Whereas the NOT gate has got only 1 input and has got 1 output. This makes the NOT gate an exceptional case when compared with the AND and the OR gates. Alright, so moving on to the next point. Why is this gate called as digital inverter? Well, when you, what we can say, read about inverter, the first thing that comes into your mind is, inverter may be like inverting the things. That's correct. The thing that is coming to your mind is absolutely correct. Inverter is the circuit that inverts the inputs that is given to it and produces the produces the favorable output. That's correct. So the question is, why is this gate called as digital inverter? That's very simple. Whatever we will give as an input to the NOT gate, exactly the inverted will be the output. That's correct. So if we give the input as 0, we will get the output as 1. And if we give the input as 1, the output will be 0. That's why this gate is called as digital inverter gate. Alright, so let's see. Oh, sir, I guess your doubt is clear. Thank you very much. So, moving on to the next one. Understanding the Boolean equation. Well, the Boolean equation is very simple. Don't go on the word. It's very simple. Let's go on to the Boolean equation. That's correct. Z is equal to X bar. Now you must be wondering, what is Z and X? I'll tell you. Z is the input. I'm sorry, correct myself. Z is the, yes, that's correct, that's correct. So what is Z? Z is the output and X is the input. When we talk about like why is that bar, or we can say a line above the X or above the input, that's pretty simple. As I've said you earlier as well, it is called as digital inverter. And why so? The statement or the equation makes it more clear. Whenever we give an input as 1, the output will be 0, and whenever we be giving the input as 0, the output will be 1. That means you are inverting the input to get the output. This is the input, correct? This is the output. You are inverting the input to get the output. Pretty much simple, ain't it? Yes, Batman. You see that? I see that. That's very simple, ain't it? It's just inverting the inputs. That's what NOT gate works on. Alright, let's go on to the next one. Yeah, Batman, yes. Alright, so let's go on to the next one. Okay, this is the explanation of the NOT gate. As you can see, this is the symbolic diagram of NOT gate. I have shown you just minutes before. And this is the truth table of the NOT gate. As you can see, I've stated earlier as well, Z is the output and X is the input. Z is equal to X bar, and the bar represents inversion. That's correct. We get an inverted, or we can say we invert the input so as to get the Z. Okay, so when we give 0 as an input, we will get an output as 1 because we have inverted the input. And when we give 1 as an input, we get 0 as an output. Okay, this is very clear when you will see the working. Now just have a look on this symbolic diagram. I will just make some animations to make it more clear. When we will give 0 as an input, we will get 1 as an output. So the first condition is pretty much clear. That's correct. The inverted output, the inverted input, you can say. Both ways are correct. And when we give 1 as an input, we get 0 as an output. Pretty simple, ain't it? It's very simple. The NOT gate is very simple. Just invert the output and we'll invert the input, you will get the output. That's correct. Yeah, you got it, man. So let's go ahead. Example to understand better. We'll take an example to understand or help you to make it understand much more better. Alright. You can see an example here. The man is shivering from cold. That's correct. Now you have a NOT gate here. At one side of the input we have written as temperature detector, that is about 20 degrees Celsius, on or off. And on the output side we have central heating, on or off. This is very simple. Just don't go on this table. I will just show you with some animations around. Alright, this is very simple. Now if we give the input as temperature, when the temperature is less than 20 degrees, that means the room is super chilled. When the room is super chilled, what will happen? What will happen to the heating in the output? Yes, the heater will turn on. That's so simple. Whenever the input will be less than 20 degrees, as you can see in the animation, we will get an output that is 1. That is basically, that's correct, central heating turns on. Okay? And what will be the next case? Your guess is perfect. Your guesses are absolutely on trot. That's correct. When you will give the input as more than 20 degrees, that is the temperature becomes more than 20 degrees, now I'm feeling a bit hot. Now what I will do is, I don't want the heater anymore to be played, or we can say on. So what I will do is turn off the heating. That's correct. That means the output becomes 0. Okay, so this is very simple example to understand. Okay, so we'll do it again for you. When the temperature goes below 20 degrees, the central heating turns on. That is, yes, basically when the room gets chilled, it's time to on the heater. And when the room is kind of warm, it's time to off the heater. That's very, very easy, and the NOT gate is understood, I guess. Yes. Now thank you very much, and meet you in the next video. So till then, bye bye and take care.